Now that we feel good about particle diagrams, let's kind of dive in and see what's contained in those spheres, right? You've got a sphere represented here, and you'll notice that there's a little bit more detail in there than we saw in the particle diagrams. Well, it turns out every single atom has all these different constituents that we're going to talk about. We're going to talk about the three subatomic particles. One of the things you'll notice about this atomic model is that there's a certain charge on kind of the outside and certain charge on the inside. Another thing which is true is that we've got this thing called a nucleus that seems to contain a couple of different things there. And you've got the kind of the outer expanse that contains these other negatively charged things. So that turns out to be super important. One of the things that I must tell you though is that this is incredibly inaccurate as in terms of an atomic model. It turns out that this nucleus is incredibly small relative to the size of this little picture right here. You wouldn't even be able to see the nucleus, right? And so we've actually expanded the nucleus so we can talk about it a little bit. And that'll be something I talk about a little bit in a future lecture here. So, first of all, what is the nucleus made up of? Well, the first thing you'll notice is there's all these little tiny positive charges in there. Those little positive things are called protons, right? And so there we can see some protons in there. Another thing which we're going to talk about in a future lecture, the number of protons is hugely important in an atom because it actually tells you what element you have. That is absolutely vital to understand early in chemistry here. So if we had this glorious cheat sheet somewhere, I wonder where I could find that. Oh, it's the periodic table. There is that whole entire periodic table is arranged according to the number of protons and things. So for instance, if I had one proton, I'm a hydrogen. If I have two protons, I'm a helium. And you kind of see that I could keep going with this, but let's stop because it's painful enough as it is. So this particular one, right, you could actually count up the number of protons, figure out exactly what we're looking at, but I don't care right now because we're just talking generally. Okay, so what the heck is that other little blue doojobby in there, right? Well, it turns out you got a whole bunch of protons, which are positively charged, and you might think, damn, that seems like it would take a lot of energy to keep together. We can talk about that. But these little neutrons right here, right? What the heck are they called? Well, they're called neutrons, right? One of the easiest things for me to play with your brain, especially as you're starting off here, is that you'll notice that the p goes with protons, right? So positive goes with protons. And it's very easy to trick people into thinking neutrons are negatively charged. No, 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 don't be that person. They are not negative, they are neutral, right? So just be careful. The p goes with p, but the n doesn't necessarily go with negative, right? So neutrally charged neutrons. So what the hell do we care about all this for? Well, it turns out that if you refer back to some previous lectures, we talked about the fact that when it comes down to understanding matter, matter is just anything that has mass and occupies space. It turns out the nucleus, its job, well, there's many jobs to a nucleus, but one curious thing about it is that all of the atom's mass is in the nucleus. The little tiny, teeny, weeny, little cute little thing has all of the mass, right? Not to say the other particles, are just basically just flitting around doing absolutely nothing to contribute to the mass. All of the atom's mass is contained in this super duper dense nucleus. That's a pretty odd thing because if you think back to us looking at different examples of matter, right? Think of us looking at that super dense mercury. It turns out that that mercury is made up of, zillions upon zillions of atoms of mercury, but I'm essentially telling you that the majority of that thing, all of the mass, is contained in these little teeny tiny little things that, have all kinds of mass, but what am I leaving out? Basically no volume, right? All of the mass is in the nucleus, but virtually none of the volume. So when you think about it, that entire bottle of mercury, or for that matter, any substance, is really mostly empty space. Whoa, far out, dude. So what the heck are these other things? Those little things are called electrons, and they're the negatively charged things. And we're going to talk a little bit about this probably in the very next lecture, is what does it mean to say that the electrons orbit the nucleus? Why the heck am I being coy and putting those in uh, quotation marks? Well, it turns out that we now understand that they don't really orbit the nucleus in the sense that like planets orbit the sun. It's just kind of a convenient way for us to think about it and to make predictions. But it turns out these things are really just kind of zipping around kind of in particular patterns. They're really oddball little things. One of the things that makes quantum mechanics, right, the science of the small, so strange is that a lot of our kind of classical rules start to break down, and electrons are so small that they actually start to have quite a bit of quantum-like character. So in other words, just small things are weird. So thinking back to the fact that matter has mass and occupies space, that's what these guys do. Most of the atom's volume is due to the electrons. That is weird. Nobody really expected this when we first started investigating the structure of an atom. So what I'm basically saying is all of the matter in the universe is essentially empty space made up of these like little zippy electrons and this super duper dense core called the nucleus. If we were actually in class, I would kind of reenact the experiments of Rutherford with a big giant ping pong cannon. I know, even my dog is impressed by this. That was Waldo, by the way. The Swiss mountain dog that likes to say things in my lectures. But anyway, we have this ping pong cannon, and what I do is that I guard myself. I have you shoot at the ping pong cannon. Sorry, I had to stop recording because my dog just ate the notes that I had in front of me. That was kind of nice. Anyway, what I do is that I have this ping pong cannon that shoots a like just subsonic ping pong ball, and I guard myself. Well, first of all my hockey pads, and then I put this like single atom thick, or what represents a single atom thick layer in front of me. And what happens inevitably is that most of those ping pong balls, hit me. And if they hit me where I don't have pads, it hurts really bad. But then every once in a while I get lucky and one of those ping pong balls hits one of the kind of the crosshatches of like the lattice I put in front of me and hits one of you. That is just plain fun. So I'll stop blabbering in just a second here, but just keep in mind, right, that we've got a nucleus made up of two different subatomic particles. The nucleus is overall positively charged. Electrons, quote unquote, orbit the nucleus and are negatively charged. And we've got this really odd thing where all of the mass is in the nucleus, all the volume is due to the electrons, and it's just a really odd model. Here's a slightly more realistic look at the way an atom actually looks with like an appropriately sized nucleus. Turns out even this is gigantic compared to the actual size of the nucleus. Like I said, you wouldn't even be able to see it. But, we're going to talk about the metric system. So when we look at this thing, which is actually a helium atom, you'll notice that the helium atom occupies, about an angstrom worth of space, which is also 100,000 femtometers. And like I said, we'll talk about the metric system in probably tomorrow's lectures. And you'll notice that this actual nucleus size is 1 femtometer, right? And so that's a heck of a lot of zeros, for the relative size of an atom relative to the nucleus. Just for fun and also to insult all the Seahawks fans out there. Sorry if you're a Seahawks fan. I did this like little calculation to figure out kind of at CenturyLink Field, which is where they lose all their games. If I put how big would the thing in the center of the 50-yard line have to be in order for kind of CenturyLink Field to kind of represent like an atom, right, appropriately. So relative to the size of like the Seahawks stadium, it turns out that an incredibly small grain of sand, not a big one, incredibly small grain of sand, if I put it right in the middle of CenturyLink Field, that's about how big the nucleus is relative to the size of most atoms. Pretty mind-boggling. So one of the questions that I had when I learned this, I was like, what the heck are you talking about? Why can't I just like push my finger through this table in front of me? And if you think about it, it actually has to do with the electrons, right? Negative charges tend to repel each other. So when you kind of, feel something, right, you're actually feeling the electron repulsion in your finger, right, which is also made up of a bunch of electrons. This is just totally wacky. This slide just kind of shows you a comparison of what the masses of these different things are. So here are different subatomic particles, protons, neutrons, and electrons. It gives you their charge. It also gives you their mass in what's called an atomic mass unit. So, first of all, atomic mass unit, this number right here, as we talk about scientific notation, is known as frigging small, right? This is crazy small, right? So if you put a period and then, or sorry, a decimal point and 23 zeros and then a 1, that's how many grams this thing weighs. So, if you want to kind of get an idea for what a gram is, there's about 5 grams in a typical nickel, right? The coin, a nickel. So anyway, really, really small, but still what you'll notice is the mass of a proton and neutron are right about the same, but that electron is incredibly small relative to mass. So these lecture slides keep going, but I always have a lot more fun actually doing kind of a chalk talk having to do with the symbols of elements. If you want to look at that second lecture supplement, it'll kind of go through it in a probably a slightly more understandable way. But at this point, we're going to switch over to, and we're going to actually start drawing some atoms on the whiteboard. I know, calm down just a little bit. I know it's exciting.